Please welcome Lieutenant Colonel Ryan Heffron.
Thank you. I'm going to start with a short story from my time serving as an experimental test pilot. So there I was, 15,000 feet in the air, flying the first full-scale jet aircraft about to be controlled by a neural network. Test, cleared to engage, agent came across the radio from the control room. I responded, test engaging in 3, and then silently counted down, 2, 1. Agent engaged, I called on the radio as I simultaneously pressed the engage button, relinquishing control of the aircraft to the neural network for the first time. For the next 10 seconds or so, everything was great. The vehicle flew smoothly. Foreshadowing, right? Then all of a sudden, an unexpected hard left bank was input, and the safety sandbox tripped off the agent, seamlessly returning control back to the safety pilot. So that was a good thing. Despite the trip, it was a successful first test point and validation that the safety system worked as expected. So what was it that caused the safety trip? Well, we trained the AI agent in simulation only. And in encountering the real world for the first time, we ran into a hydraulic pressure differential problem caused by the shape of the control input and the way it interacted with the hydraulic system. Because we had a trusted safety sandbox on board, we proceeded with about 30 other test points on that sortie, with at least half resulting in some kind of trip being activated. Whenever you go and touch the real world for the first time, there are always a lot of unexpected events. A successful first sortie complete. We landed, debriefed, and dove directly into the data. Late into the night, we'd already solved that original issue along with a myriad of others, and we were ready to go out the next day and fly again. And so now at DARPA, I've had the lucky privilege as a program manager to build on my experiences that I gained as a test pilot previously, flying high-performance aircraft and also developing AI-driven autonomy. And today I want to pass along a lesson I've learned, which I think is important for developing autonomous systems, especially ones that interact with the real world. I call it closing the loop on learning. At a high level, almost all autonomous systems, they follow a loop. We in the Air Force know it as the OODA loop, observe, orient, decide, and act. In the robotics community, it's also known as the sense, plan, and act loop. At a high level, these are the decisions we as humans have to make when we learn a new task. However, over time, these decisions become automatic. I expect not many of you have to consciously consider coming to a stop at a stop sign at an intersection. Rather, neuroscience research shows us that many behaviors become an automatic learned representation by our brains. And we only focus in on things that don't match our subconscious expectation. It's the constant prediction of future states in a subconscious world model that enables us to effortlessly perform so many tasks so well. We only have to attend to the differences between our expectation and the experienced reality. This, however, is where autonomous systems tend to break down today. They're unable to generalize to an unexpected situation because they can't close the loop between their modeled world and the real world. This was part of those early problems that we ran into on the sortie I just described. Moving forward, we need to develop methodologies to seamlessly identify representational gaps and find ways to close those gaps in real time. Today, traditional approaches to this challenge involve creating high-fidelity physics-based models, but all too often we focus on the wrong aspects of the modeling and we fail to continuously close the loop with the real world. With the recent successes using deep reinforcement learning and other machine learning approaches to train AI agents to perform tasks, model predictivity has become far more important than model fidelity. And what I mean by model predictivity is that the performance gains or losses that are experienced during training in a simulation environment are reflected in real-world performance. This is absolutely critical for the DoD because we have a unique mission with an adversarial component. We will never be able to fully test our approach in the real-world environment until we find ourselves in a conflict. At that point, we'll need to rapidly close the loop on learning if we're going to successfully utilize learning-based autonomous capabilities with appropriate human oversight. If you find this area exciting and want to join me in developing autonomous capabilities for fighter aircraft, keep your eye out for future opportunities to work with DARPA.